So good morning. This is the introduction to microscopy on the Morel Instruments Nikon TE2000U here at the Harlem Biospace. Today we're going to be going over some of the hardware that we have here on the microscope and some of the techniques that we're going to use in order to take some pictures and really get understanding, familiarized with the microscope itself. What we have here on the scope itself is we have our diascopic pillar, we have a condenser, we have a diascopic light source or transmitted light source. We have the camera here on the left side. This is a color camera, a DSLR-I1. We have our eyepieces here where we can adjust them for our correct diopter, the distance, the interpupillary distance. This is for the diopter adjust. On the right side of the microscope here, we have our beam splitter that adjusts from the eye position to our left 100 position. Position 5 is our left 100. That'll send all of our data to the camera. Position 1 will send all of our data to the eye. We have an optivar here that goes from 1x to 1.5x, so it squeezes out a little extra magnification. We have our focus knob here. This is our coarse adjustment, our fine adjustment. And then we also have our turret, our fluorescence turret. And this has our fluorescence turret cubes inside. We have one for FITSI, which generates blue light. We have one for TRITSI, which generates green light. We have a UV version, which is for DAPI. And we have an empty slot for our bright field applications. This over here is the stalk for our stage. So we can adjust our X and Y positioning here. A little bit further back, we have our illuminator for our fluorescence aspect. We have our liquid light guide, which comes off of our fluorescence light source here, sends the light directly into the back of the microscope. This is for fluorescence, in which case what we would do is we would shift our turret from one bright field cube to our UV cube, or our blue light cube, or our green light cube. When there is no cube, it's all bright field. Our light goes straight from up here, straight down through your specimen to the objective beneath, and eventually through all the mirrors and lenses inside of the stand itself, and out either to the camera over there, or directly up to the eyes. At this point, now that we've looked at our microscope and the hardware that we have on it, we're going to get started with our first lesson today, which is understanding phase contrast microscopy. Phase contrast microscopy is used for samples that don't have any staining. It's basically a contrast method that uses a phase shift between two optical interference points that actually generate contrast where you wouldn't otherwise have any. It's one of the simplest and earliest forms of generating contrast. It's an inexpensive way of generating contrast, and it uses a few different parts all in combination together to generate an image. In order to do phase contrast microscopy, you need phase objectives. One of the objectives says on it clearly pH1. And inside of the objective, you actually have a ring that we'll be able to take a look at a little bit later. That ring is made of a material that retards the light. In order to do correct phase contrast imaging, you need a phase ring inside of your objective, and you need a phase annulus inside of your condenser right here. Our condenser here is labeled with an A for all the light, PHL for a particular type of phase objective, pH1 for other types, pH2 for yet another type, and back to C for a closed position in order to use with our fluorescence. We'll come back to that later. On our A, we actually have an aperture here that we can adjust, open and closed. Normally keep it about midway. In our system, where we're discussing phase contrast imaging, we'd have our light starting at our diascopic halogen area over here. We're going to send light straight through to the front this way. We have a mirror that directs the light straight down through your condenser, through the annulus in your condenser. through your specimen, and then the rest of it goes right to the objective. Inside of your objective, your phase ring is going to retard some of that light, and only the annulus ring light is going to get through. What you will see at the end of it is as the light goes down through the system, we can either change to our camera or to our eyepieces, and we'd be able to see what we're looking for. This is an especially good and inexpensive method for an easy method for looking at unstained samples. When you have stained samples, you actually can pull out more detail than you otherwise would without any sort of contrast method. So our first step in doing any sort of microscopy imaging or observation is color illumination. Color illumination is a method, or color alignment rather, is a method for generating the best possible light path for your specimen so that you can get the truly best image and the truly representative image of the product that you're trying to look at. To do this, there's an easy stepwise procedure. So the first thing that we will do is we'll make sure that our light is on, which as we can see it is on. We have some light coming through. Our next step is to observe our specimen and make sure that it's in focus. And I can see a little bit of pink, which is what we're actually looking at. It is a stained specimen. So I'm going to bring it into focus here with our coarse focus. It's nice and sharp. I'm going to just, using my stage handle, and move over to have my specimen centered where I want to see it. I'm adjusting my fine focus now. See it nice and sharp through the eyepieces. Our next step is to shrink down our field of view. So we use this this diaphragm up at the top, and we slide it down as small as we can make it. While doing that, what I'm seeing through the eyepieces is my octagon of light. The leaves inside of this diaphragm have compressed down to a very, very small pinpoint of light. And now that my specimen is in focus, I need to get that octagon into focus. In order to do that, I utilize this knob here on the condenser, this condenser adjustment knob. And in order to do the most ideal imaging, I'm actually going to remove my phase ring, which was in place before, going back to A. I'm going to limit the light that's going through. And now, once again, I'm going to make sure that my specimen is sharply focused, and it is. The next step is I'm going to make sure that my condenser position yields the best focus. And then I'm going to adjust here. We have two screws, positioning screws, on the condenser itself, right here. And these are spring-loaded screws that basically push the octagon of light around, left, right. The idea is to get it as centered as possible. Once it is, we go back up to our diaphragm up here, and we start to open it up. And as we open it up, we should be able to see that our centered light is indeed centered, and it is. And I'm going to open it up just past. We don't have to open it all the way. We can open it just enough so that what I'm observing is fully illuminated. This ensures that we have the correct amount of light going to your specimen. Too much light will actually generate what's called scatter, and you won't get as sharp of an image as you possibly can. The next step would be to go and look at this through our software, where we would have a live image showing the exact same thing. So what I'm now doing is I'm going to be doing our color illumination, a color alignment illumination, on the screen so we can see what things would look like if we didn't have eyepieces. So I've switched my beam splitter over to my 5 position, which is the camera on the left side. Now I'm going to go live. I'm going to hit the play button on our software and go live. And what we see here is a stained specimen. But it's not in focus. So what we want to do is we want to first, according to our color illumination protocol, we're going to adjust focus. So what I'm doing right now is I'm adjusting the coarse focus. I'm adjusting our fine focus. The next step is to shrink down our diaphragm so that we can see our little octagon of light. There it is. And as you can see, it's not perfectly sharp on the edges there. If I adjust our knob here, we can get it to a sharp representation. I'm limiting the amount of light so that we can get it as sharp as possible. And now that it's nice and sharp, the next step is to adjust using our thumb screws here. Our thumb screws here, we can actually move this around the field. So this is obviously not centered. We want to get it as close to the center as possible. And then as we, and now that everything is sharp and is close to the center, we can open up our field diaphragm slowly. And as you can see, we're still not perfectly centered. So we're going to adjust this a little bit further. I'm going to open up a little more. And we're going to open it up fully, just beyond the amount of camera. And now we have a very crisp, clean image. And this isn't even with phase contrast. This is just our standard stained preview of our slide. To go to phase contrast, if we wanted to, since we're already on a phase objective, it's our 10x phase 1, we would switch on our condenser here. We can go over to pH1 so that they are matched. And we've just created a tremendous amount more contrast. Nice, sharp image with detail. We can see everything. So what we're doing today is we're going to go and do a phase contrast image. So what we do with this is we put our specimen on our stage and we start observing through the eyepieces to find our specimen in the eyepieces. Now I've actually done that. We have our stage moved, everything is where it belongs. I can see my specimen nice and clear. I'm going to sharpen it up perfectly with my focus here, my fine focus. It's nice, sharp as a tack. Now I'm going to make sure that my phase image, my phase ring is correct. And it is. Phase 1 matches our 10x objective phase 1 in there. And so what I have is a nice clean image that when I want to take an image of it with the camera, I would just switch over from my eye position here, position 1, and switch over to position 5. If we wanted a higher magnification image, we could switch from our 10x to our 20x. I'm going to put a slightly different specimen on here. Got it right in position. Go once again, bring it back to the eye pieces. I can see my specimen. I'm going to get it to an interesting area, and I'm going to focus. Now I'm nicely focused, but I'm still on my 10x. Oh, I'm on my 20x. So I have a nice image there. And now if I wanted to take a picture of that, I could go and change my beam splitter here, position 1 to position 5, and then we'd go and observe on the camera side over at the software. We're now all familiar with our parts of the microscope that generate phase contrast images to the eyes. We now are going to go and use our software and take images using phase contrast and the camera. So our first step is we're going to get a sample into focus. We can do this on the screen by going to live. We have an image on the screen. We are going to get our specimen into focus by using the coarse adjust. So So we are now in focus. I also want to note that across the top here on our optical configurations of the software, we have a 4x, 10x, 20, 40. We're on the 10x objective, and so we're going to click 10x. What that's going to do is it's going to tell the software that we have a 10x objective, and that's going to make sure that all of the metadata, the scaling of the image, the size of the image, the pixel size relative to all the tissue itself, these are all going to be programmed into any image that we generate from this software. This makes it especially easy if we want to do something like add a scale bar, which we have right over here. We've just added a scale bar very simply, and it's correct because we're using the correct objective optical configuration. This is an incredibly powerful tool and saves you a lot of time when people go and try using Photoshop to do the same sort of technique. So we've put another specimen on the stage platform. I'm going to go live, and we're looking at something else here. So as we can see, we're not really in focus. We're going to get it back into focus. Here we have some nice contrast. We need to make sure that our exposure time is correct. It seems that we're using a 2.7 millisecond exposure time, and our light is not at the maximum. If we were having a hard time looking at the light, we could add more light, and we could adjust our exposure time to be a little bit shorter. Or we can just use auto exposure once. And what that does is that evaluates the entire field. We can click that again and no longer are doing auto exposure. As we can see, we have a nice clean image. So all we have to do is take a snap by clicking this snap or capture button here. And it takes a picture. And now we have our captured image here. We're no longer live. And we have an actual captured 10x image. We have our scale bar on here. That's correct. And we can observe a lot of different things inside of actually our image simply by zooming in with the scroll wheel on the mouse. This is a digital zoom. The image has already been captured. If we wanted to go to a higher magnification, all we would have to do is adjust that on the microscope itself. And then remember that we actually want to adjust which objective method we're using. So for example, if I switch over to our 20x objective from here, our 20x objective is still a phase 1 objective. We don't have to adjust anything on our condenser. We can go live, and we may have to adjust the focus and the exposure time a little bit. I'm going to maximize this so we can see it. What we're looking at is not that same borderline. There, at least we can get some more contrast. I'm adjusting the fine focus now, and we could definitely use a little more light. We can go with an auto exposure and actually increase the exposure time, or we can use, there's a gain feature on the camera itself that increases the sensitivity of the camera. Now we have a nice image with some detail that we'd like to see, nice and focused. Again, we can take a capture image there. Oh, the only thing I forgot to do here was the 20x. We'll fix that. It's not responding for some reason. We would click the 20x and make sure that we're using the right objective for the software. Capture that image. And now we have a 20x image. Here. Now it still says 10x. We have to fix the software. So I'm going to do that. But as you see, we have a nice higher magnification image. We can go even further with a 40x. So our next part of the lesson plan is going to be doing some fluorescence imaging. So in order to do that, we want to get our specimen correct, put onto the stage in the proper position, and we're going to be using our fluorescence light source and cube combination in order to generate a 3-channel image. So to do a 3-channel image, we'll want to look at our DAPI, we'll want to take the image, we'll want to look at our FITSI, we'll take the image, we'll want to look at our TRITSI and take that image, and then we'll merge them together using the software. So here I'm showing us a fluorescence cube. So this is what makes fluorescence imaging and fluorescence observation possible. There's 3 parts to this cube, 3 pieces of glass, and all of them behave together to generate your fluorescence image. What we have here to begin with is our exciter. So this is an exciter filter where the light coming from the fluorescence source immediately goes through. This automatically limits the wavelengths of light that are actually going to the specimen. Now right now we have this upside down because we're on an inverted scope. We do it this way. So here's our light coming in to our exciter. And then we have a dichroic mirror where that allows some light to reflect and other light to pass directly through. So what we have here is, in this position, we'll have light coming through the back, straight through. It's going to reflect off of this mirror at this position and go upward towards our specimen. It's going to hit our specimen, and the specimen is going to fluoresce. After fluorescence, it will emit another color light of a longer wavelength, lower energy. That light is actually going to be passing back through the dichroic mirror, and it's going to hit that mirror here, our barrier filter or emitter filter. And what comes through that emitter filter is your fluorescence signal. That's what we can actually see. And when a cube is constructed well and matched very well to the fluorochromes that you're using, you have a very, very nice signal to noise ratio where you can get lots of signal and 0 noise. We'll take a look at this in the presentation. We have a little bit more info, but for the most part, that's how we get our fluorescence to work. Without the cubes, is a much more cumbersome procedure. This makes it a more compact, easy to use system. So what we're looking at here is our fluorescence light source. Now if we want to do fluorescence imaging, we need to turn our fluorescence light source on. So we're going to get started by doing that with this switch right here. So we've turned on our fluorescence light source, and it's going to warm up and eventually going to send light down the light guide straight into the back of the microscope. So as you can see, we're currently using brightfield light. You can actually see that hole in there where the phase annulus is. If I turn this to all, to A, you see that that's no longer there. You can actually increase the size of that. We're actually going to move this over to C because when we're using fluorescence, we don't actually need anything above the above the stage itself other than the specimen. For fluorescence, we don't care about anything above the specimen. We're not using any transmitted light. We're only using light that comes from our fluorescence light source, goes through the back, towards the front, reflects off of a fluorescence cube, and it sends light straight up, excitation light straight up to your specimen. Your specimen emits light of a lower wavelength, of a longer wavelength, and then that remaining light goes down through the system and either gets shunted over to the eyepieces or to the camera, depending on what we'd like to do. For simple observation, we would just go to the eyes, but if we wanted to document it, we would go to the camera. Here we have a slide that's professionally done. There's no staining on there, yet there are some cells in there. We can't see anything on there. There's no contrast or anything. Everything that's going to be illuminated is going to be illuminated with the fluorescence light, and anything that we're going to see is going to be reflected from that fluorescence light. So I'll put my specimen down again. So right here we're looking at our fluorescence light source. We've turned it on already so that it can warm up. We have a shutter on the front. Okay. Currently we have the shutter closed because we don't want to send any light through the light guide into the back of the microscope here. What happens is our light goes into the back of the microscope. It gets reflected by some mirrors in the back here, goes straight down towards the front. The light goes towards the front. It goes through our filter cube turret, and that's where our fluorescence magic actually happens. So currently we're on a bright field or an empty position, so we wouldn't actually see any light reflected. But if we go over to our UV, and UV is not going to be the easiest one to see at this point, but if we go over to our UV and we open up our shutter, you can hear it, we're actually sending some light through. And you can just barely observe this pinpoint of light. But you can see that we're actually getting quite a bit of light going through. This is it's a violet light. It's basically a UV. So what I'm seeing in the eyepieces here is some what's called reflected light, but it's fluorescence. I'm getting an actual fluorescence signal. And what we would do is we would send that over to the camera so that we'd be able to see what we're trying to observe. So I'm going to do that. I'm going to change this beam splitter over to our position 5. And I'm going to go and take a look at what we see on the screen using the software. I'm currently on the 20x objective. I'm going to switch that over to the 10x non-phase objective. And I'm going to go live. And here we have a signal. This is a DAPI signal of some cells at 10x. As we can see, I can move around, go to some more interesting areas. Some of this is nicely stained and some of it is not. This is what we'd expect to see. We're also at a relatively short exposure time right now. So we can actually increase our gain a little bit and lower our exposure time even more. The less exposure time, or the shorter the exposure time, the better our cells fare. So now here we have a nice little vessel. This is probably going to fluoresce very lovely in other wavelengths. So we're looking at our DAPI. What I'm going to do is I'm going to take a picture of our DAPI. So we snap it. Moving on to change the filter cube, we've taken one DAPI image, or one UV image. I'm going to move our cube's position to our GFP, or FITSI position, and I'm going to take a look through the eyepieces to see what we have. So what I'm seeing here is a very nice piece of the tissue. I'm going to send that over back to the camera again. I'm just going to go quick live. And you'll notice that it's green. We have a high exposure time here. I'm going to lower that a bit. This is more like what we should see. I'm going to adjust the focus a little bit here. Okay, so I'm going to take this picture too. Notice we haven't moved anything positionally. We've only just adjusted focus and the exposure time. I'm going to snap that one. And then finally, I'm going to change the filter cube position. And we're going to go live again. And it doesn't look like there's much here. We're going to increase our exposure time a bit. And it looks like this particular wavelength isn't terribly bright, in which case what this means is that it's not specific. This is not a true fluorescence. This is basically autofluorescence, what's called autofluorescence. I'm going to go back down to our 60 millisecond mark. We don't have anything there. I'm not even going to take the picture. I'm going to close our shutter over here. And now we no longer have light going to our specimen, and we're not doing what's called bleaching our specimen. At this point, that would be the image, and we would move on to our processing itself on the software. So we have here a captured 10x and a captured 10x1. These are by default labeled. What we can do is I can click one of these, make it a little bit smaller so we can see what we're looking at here. and we'll merge these. So we'll go to our file drop down, merge channels, and click this, and our green component is captured 10:1. Our blue component is captured 10x. And then we just click OK. And now we have an overlaid image where our green and our blue are shown together, merged. From there, if we wanted, we can add a scale bar to that. And I believe that it's the wrong color. I'm just going to change that real quick. Yes, we had a black one. I'll change it to red. And here we are. So with this, we've generated a color image, a multi-channel color image, using 2 independent channels. And all we did was just adjust our filter cube turret in order to make that happen. At this point, we could save this. And call this merged, D and F for Dappy Fitzy. We could save it as a JPEG or TIFF, or an ND2 is ideal because that's our Nikon format. It has all of the metadata that we discussed earlier. And I can just click it, save. We'll ask you if there's anything extra you want to save. Click OK. We now have a saved image, merged DF ND2.